This is Magic A06, differentiable manifolds. I'm Kirill Mackenzie, and this podcast is about tangent vectors on a manifold M. So we've got M, and we've got a point M0 in M. And I define a tangent vector to be a map from the smooth functions on the whole manifold to R that is it's additive, first of all, and it's linear over the reals, and it satisfies this derivation equation here for all smooth functions f and g and all constants a in R. And that's what we saw as a characterization of tangent vectors on Rn. And we'll see that this works. We'll see, in fact, that the other formulations also carry through. So one thing to notice, first of all, is that if you apply x to the function that's constant at 1, then from the derivation equation, you immediately get 0. And therefore, by the linearity over the reals, any constant function at all gives 0. And of course you expect this because it's a differential operator, but just the same, it's worth noting that that's where it comes, how it turns out. So if I've got two such capital X, or capital X and a capital Y, then their sum clearly satisfies the same three equations. And if I multiply one of them by a real number, then again it satisfies the same three equations. So these tangent vectors form a vector space, and that's the tangent space at M0, and a fairly standard notation is capital T sub M0. Spivak just writes M with M0 as the subscript, and this is it's not exactly common, but it's used by quite a lot of people. But as we go on, we'll see that it really is valuable to have the capital T to do things with. So that's it. That's the definition of the tangent space to M at a particular point. Now, here's the other formulation that works on Rn. That's to say, derivatives of curves. Suppose we've got a curve gamma in M, and suppose that it goes through the point M0 at time t equals 0. And I define a capital X, which is going to be a tangent vector, by saying that capital X operated on a function f is the derivative of f comp gamma. And f comp gamma is just a function from reals to reals, so that's just the ordinary derivative taken at 0. And it's a very quick check that satisfies the three equations on the previous frame, the previous slide, and therefore that really does define a tangent vector. So we'll usually denote it by gamma dot, Newton notation at 0. It's tempting to denote it by d dt of gamma t at 0, and some people do this, and indeed I've done it in the past. But it is misleading because when one looks at this sort of expression, one tends to assume that it's the limit as t goes to 0 of gamma t minus gamma 0 over t, and of course on a manifold that makes nonsense. Indeed, even on a submanifold of Rn, it usually is nonsense. So we'll avoid this notation. We'll stick with this one here. Okay. Now So two things. First of all, we want to know how this looks in a coordinate system. And secondly, we also want to know what the dimension of the tangent space is. Of course, we expect it to be the dimension of the manifold itself, but we haven't actually proved that. So take a chart. I'll just write phi, just a single chart, defined on an open set U, and taking values in Rn, and a tangent vector x, capital X, at a point m0. And then I'm going to define a tangent vector on Rn. I'll write x prime simply by using the chart to pull the functions on Rn back to functions on the manifold. Okay. So x prime of f is defined for f, a smooth function on Rn, and it's defined in terms of the effect of x on smooth functions on M. So again, it's an immediate check that x prime really is a tangent vector, and so by what we did in the previous podcast, it's a sum of n terms where n is the dimension of the manifold, constants times the partial derivatives with respect to the coordinate functions. So perhaps I should have spelt out here. Ooh, let's change colours. Right, I have changed colours. So phi of m, I'm thinking of as x upper 1 m down to x upper n m. Okay. So that's the tangent vector. X prime is the tangent vector on Rn. We know that the tangent spaces to Rn are simply other copies of Rn, and that every tangent vector at a particular point can be written in this fashion. So that establishes that the dimension of the tangent space is indeed the dimension of the manifold. Okay. So another way of looking at the local representations of the tangent space is to define curves in terms of the coordinates. So I take an I between 1 and n, and I define a curve gamma I in M by gamma I of t is phi inverse of zeros in all the places except for t in the ith place. And this is assuming, by the way, that phi of my point m0, phi of that point is actually the zero of Rn. But one can always arrange that. It's not really a big deal, but for convenience we'll do it like this now. So phi I of t is a curve in the manifold, and it goes through m0 at time t equals 0. And the derivative, or the derivatives, form a basis for the tangent space because we know that the curves in Rn, just given by this, derivatives along those lines form a basis for the tangent space to Rn. So we can prove this independently that they form a basis, but I think it's clear from this description now. So the gamma dot I0 form a basis. And I'll often use this short notation, just a partial symbol sub I with an alpha when we're working with more than one chart, and we've got a chart denoted phi alpha. Okay, so more about tangent vectors in the next podcast, but that's all for now.